Welcome to our keynote on unlocking the key to distributed Postgres. In this keynote, we have one exciting announcement, one technical talk, and one video all together. Marco and I will be co-presenting this keynote. I'm Ozgun, the CTO at Citus Data. Prior to Citus, I was in the distributed systems engineering team at Amazon.com. And I love drinking margaritas at the beach. Marketing seems to have cut down my slide, but the beach is a critical part of my margarita experience. And Marco is a principal engineer at Citus Data. Marco holds a PhD in distributed systems and previously worked at AWS. Marco loves the color orange, well, because he's Dutch. We work at Citus Data, where we focus on scaling out Postgres and making sharding simple, so you can focus on your application and not your database. If you aren't familiar with Citus, there are just a few things to know before we dive into this story of unlocking the key to distributed Postgres. We love Postgres, and we package Citus as an extension. So we're not a fork, and we can stay up to date with all the latest features in Postgres. And we make Citus available in 3 different ways. First, as open source. Second, as a fully managed database service on AWS. Third, as enterprise software. At Citus Data, every single engineer on our team shares the same mission: to make it so that you never have to worry about scaling your database again. Well, what does that mean? I was watching a talk at the AWS Summit last year. At the beginning of the talk, second or third slide, there was a simple decision tree that described how you should pick your database. If you need the power and performance, go with a relational database. If you care more about scaling, pick a NoSQL database. But the NoSQL land here is tricky. We've heard over and over again that customers would start with NoSQL, then at some point, they'd need transactions. Or you have 2 collections only if you could join them together. What you want, and what everyone wants, is the powerful features of relational databases with the elastic scale of NoSQL. If everyone wants this, why don't we have it? Because scaling relational databases is hard. What makes it hard? This is the Postgres 9.6 manual in printed form. It's 3,558 pages of features built over 2 decades. For a Postgres user, all of the features they use need to linearly scale. And it isn't only this manual. You have many Postgres clients, GUIs, and frameworks that combine these features in unimaginable ways. So how do you take a solid relational database and make sure that all of these complex features scale? You do it one by one. You break down one seemingly intractable problem into 500 smaller ones, and you implement these features one by one. 2 years ago, we were on this stage at this conference. We announced that Citus was going to be open source. After that announcement, we talked to many of you about scaling your relational database. In every conversation, we'd hear about different Postgres features that needed to scale out of the box. Your feedback helped us learn more and prioritize these features over the past 2 years. Today, we're excited to announce Citus 7.0. Citus 7 marks a major milestone in our journey to scale Postgres. After our open source announcement, you told us 3 things. 1, transactions, transactions, and transactions. You also told us taking your application and your application framework, pointing it to Citus, and having everything just work was key. Finally, a distributed database is only as good as the database it builds on. Citus 7 comes with support for the upcoming version of Postgres, Postgres 10. All of these features and themes are exciting, But I'd like to zoom into one of them, transactions in Citus. And as a clarification, every table and feature you see in this transaction block, this overwhelming transaction block, runs across distributed tables and reference tables as is. You don't need to make any changes to your application. Of course, no reasonable human being would write this transaction block. This example transaction comes from Active Record. In particular, unit tests in Rails use save points, which are at the top there, to model nested transactions. In this example, in addition to nested transactions, you see sequences, joins, insert into returning, distincts, and many other things. And executing this nested transaction block in a distributed environment isn't even the tricky part. What happens when you have many of those transactions running concurrently? If those concurrent transactions modify database tables in different orders, your database may run into a deadlock. Postgres resolves deadlocks for you on a single machine. But what happens when your tables are scattered across machines? How do you detect deadlocks in a distributed database? Fortunately, you don't even need to worry about this. We solve this problem for you in Citus 7. And I'd like to introduce our principal engineer, Marco Slot, to the stage. Marco lives, dreams, and breathes in distributed transactions, and he'll explain how we implemented distributed deadlock detection.
Thanks, Ozgun. So when we set out to implement distributed transactions in Citus, it turns out one of the trickiest things we need to deal with is a very simple thing that's very important to databases, namely locks. So locks protect concurrent access to the same data. It prevents two transactions from modifying the same row at the same time, for example. But in databases, transactions can be very complicated and grab many different locks. And at some point, they could even end up waiting for each other. And that's known as a deadlock. And this is a very bad situation that needs to be dealt with. Otherwise, you cannot really reliably run your database. So if we zoom in a bit on when do you run into locks in Postgres? Well, there's many different cases. Pretty much any command that you do grabs some locks usually. But one example is the row level lock. So if you update a row in Postgres, that update grabs a lock, and any concurrent transaction that tries to update the same row will then block until the first transaction is finished, which means it either commits or aborts. And then after commit or aborts, all the locks are released and the second transaction can continue. Now, if two transactions don't modify the same row because their filters aren't conflicting, they can run concurrently, which is very nice about Postgres. It has great write throughput. But maybe later in the transaction, you do something that does conflict with an ongoing transaction. So then you still block. But now, while you're blocking, the second transaction on the right is also still holding on to the locks that it acquired in the first statement. Okay. But then what happens if the first transaction actually also tries to modify that row? So they both modify the same rows, but in a different order. And the transaction on the right holds the locks on the rows where x equals 2, and the transaction on the left holds the locks where x equals 1, and now they're waiting for each other. There's no way out of this situation. There's no way to get both these transactions to commit, because neither of them can continue. And this is a deadlock. And the reason deadlocks are particularly bad is because not only do these two transactions get stuck, any new transaction that comes in and tries to acquire one of the locks that these transactions hold will also block. And maybe that transaction will block other transactions. And so a deadlock can actually escalate into a full system outage if left unchecked, where all the processes are blocked. Now, the way Postgres deals with this, of course, Postgres has to solve this problem. So in Postgres, if a transaction is stuck waiting for a lock for more than 1 second, it runs the deadlock detection code. And the deadlock detection gathers the lock graph across all processes, or the lock tables across all processes, and then builds a graph where each node is a transaction, and the edge says this transaction is waiting for this other transaction. And then if there is a cycle in this graph, it knows there is a deadlock, and it cancels some of the transactions until the cycle is gone. So in this case, it might cancel one of the transactions performing the update. That ends the transaction, meaning the locks are released, and then other transactions which are blocked waiting can now continue and finish. So one dies and the other lives. In Citus, we also support transactions, so you can do begin, update, update. But Citus delegates transactions to the nodes which actually store the shards of your distributed tables. So if, for example, on the coordinator you do 2 transaction blocks with updates in opposite order, and that gets delegated to node 1, then if those transactions create a deadlock, node 1 will say, there's a cycle in the lock graph. I'm going to cancel one of the transactions. That sends back an error message to the coordinator, which will then abort the whole transaction, and the other transactions that are blocked can continue running. So, okay, that works. But now what if the transaction actually spans across multiple nodes? So one of my rows is on node 1 and another node is on node 3. So transaction D1 is waiting for D2 on node 1, and D2 is waiting for D1 on node 3. The coordinator is just waiting to get a response for the queries that it sent to these nodes. And Postgres doesn't see a deadlock. Node 3 doesn't have a deadlock. Node 1 doesn't have a deadlock. The coordinator doesn't have a deadlock. But if you look at the whole picture, there is a deadlock. And so this is the situation we have to deal with in order to safely support distributed transactions. And so what we did in Citus 7 is add a new component to Citus, which is the Deadlock Detector. This runs as a background worker as part of the extension. And if a distributed transaction gets stuck, it gathers all the lock tables from all the nodes over the network and then starts building a distributed transaction graph. So it associates the transactions that go on the nodes with a distributed transaction on the coordinator, and then sees, oh, this distributed transaction is waiting for this distributed transaction on node 3. And then it can then perform the deadlock detection on that graph, and it will see the cycle, and it can then cancel the transaction on the coordinator, which will abort it on the nodes as well, and then the other distributed transaction can continue. So this is necessary for implementing distributed transactions on a sharded database safely. So as of Citus 7, we can support arbitrary transaction blocks. Previous version could already do transaction blocks where every statement goes to the same node. In Citus 7, that restriction is gone. You can now do transactions across all the nodes. Now, you might be wondering, well, I can do this in Postgres already, so what is actually the benefit of Citus? As to show you that, I've put together a little demo yesterday of which I made a video to show you that. So I'm going to change to the video and full screen. Right. So the easiest way to get started with Citus is using Citus Cloud. You can simply say, give me a cluster of 4 Postgres servers, 4 cores each, enter the name of the cluster, and go. And then after about 10 minutes, you get to the dashboard where you can find how to connect to your cluster, monitor the individual nodes, and do operations like adding a new node. So now let's do a side-by-side comparison of running the same commands on just regular Postgres and Postgres with the Citus extension. So on Citus, you make a table distributed by calling the create distributed table function, where you specify the partition column. And this goes and creates the shards on the other nodes and make sure that Citus handles all the queries. So we'll first load some data, about 1 million rows, into a table, and then create an index. And this is already something where we can see Citus providing benefit, where it can actually parallelize the create index across the entire cluster. Whereas doing that on a single core, especially a GIN index, can be very expensive. Same with analytical queries. Citus can parallelize those across all the shards and get really high speed-ups for analytical queries. Also, now that we've created an index, actually indexes can really become an ingestion bottleneck on Postgres. But actually, if you shard your data, that becomes much less of an issue because the work can be distributed. So data loading also becomes faster once you have indexes. Now, where Citus becomes especially beneficial if you have so much data that it doesn't easily fit in memory, and you're often reading from disk. And so we're doing PG bench with scale factor 10,000, generates over 100 gigs of data, and then doing a select benchmark. Now, on Postgres, it will often have to go to disk, which makes throughput pretty bad and latency bad, which really affects your users, your application. Whereas on the Citus side, we can always have enough nodes to fit the data in memory and keep our latencies down and our throughputs high. We can also do like PG bench, where it does small transactions. It can do that as a high rate as well. We also get some speed up there. And so let's look at an example where some of the new Citus 7 features with an ad campaign management data model. So we've added features for bulk insert, multi-valued insert, and updates with subselects, and last but not least, distributed transactions. So that means a lot more of the features that you use, that your application might rely on in Postgres, can now be directly used on distributed Citus table. And the big advantage that you get is that if a day comes when you're running into performance issues, you can just add more nodes and make the performance issues go away. So that's kind of what we have been working on. And let's see how we get back. So in Citus 7, we looked at what are our customers saying, what are their applications doing, which features do we need to support. And so we now support distributed transactions, multi-valued inserts, save points, and if you have a SaaS application that runs on Rails or Django, it's now easier than ever to convert it from Postgres to Citus, which often involves like adding some columns to be able to shard on tenant ID. So if you have a SaaS application, check out Citus. Citus 7 is available now in our package repo. It's on GitHub, and it's in Citus Cloud. And if you have any questions, we'll be at the booth. Thank you very much for your attention, and thanks, Ozgun.